management and water saving are evolving as a crucial factor in the context of growing demand and sustainable development. Since the irrigated agriculture sector is the major consumer of freshwater resources for food production, it is important to manage the available fresh water optimally to save water for other purposes and also to increase the crop yield. The major challenge in the Indian irrigated agriculture sector is the very low irrigation efficiency and mismanagement of water. In addition to this, the utilized irrigation potential of the nation is 85 million hectares, whereas the ultimate irrigation potential is 140 million hectares. This ensures the need for irrigation performance assessment to identify and manage usable water for attaining potential water saving strategy. The evaluation of the irrigated system needs thorough knowledge on the hydrological cycle in the crop water soil continuum. Thus, it involves quantification of land water use and crop water consumption throughout the growing season from farm plot level to river basin scale. The analytical tools such as the hydrological models, which is the simplification of real-world system, can be used to estimate the water balance components. One of the key arguments in modeling and investigating the land-water interaction is the lack of ground-measured data. Moreover, most of the Indian basins are in hydrologically data-poor conditions. Thus, to make up for the limitations in the ground-measured data, we rely on the remote sensing data acquired from the satellite. Along with it, the semi-distributed agro-hydrological models, namely soil water assessment tool SWAT, has been used to investigate the land water change by modeling the hydrological responses with the easily available topography, climate data, soils and land uses. Water withdrawals for irrigation purpose in semi-arid regions enhances the ET and decreases the river discharge. ET component varies across the location with respect to the cropping pattern, climatic conditions, water availability and crop growth period. Thus, the spatial and temporal cropping information plays a major role in hydrological cycle in estimating the water use by agricultural system. The time series of 16-day composite of normalized difference vegetation indices, that is the NDVA, obtained from the Moody's satellite provides an excellent scope to extract the cropping pattern, crop sowing and harvesting dates, and long-term agricultural practices over the basin in a reasonable spatial and temporal scales. This land management practices incorporated to the model helps in representing the field conditions to estimate the ET or the consumptive use along the basin accurately. Beside the calibration of the hydrological model using the spatial and temporal ET data along with the discharge data representing the real-world hydrological process. With this, the hydrological setup, the performance of the river basin is evaluated by estimating the performance indicators such as the irrigation efficiency, which is ratio between water diverted from the source to the consumptive water use by crops, and water productivity, that is the crop yield per consumptive use of water. The results from this study will allow to identify the current status of the basin water use. With this detailed hydrological setup, the various scenarios of cropping pattern and management practices can be adopted to improve the irrigation efficiency and water productivity, which may lead to water saving in the basin scale by reducing the non-beneficial water losses. Thank you.